Okay. So yeah, just a little bit more about the exam upcoming next week. It will be very similar to your homeworks. So when you do your homeworks, maybe you felt not so confident about like the time you spent working on the homework, or the way like you work through the questions. But at this point, I'm about to see that make sure you right now you figure out how to solve those problems. Like I'm thinking, yeah, for the yeah, either come to the office hour. Like right now, the office hour are my office hour are virtual, and for the teaching assistant, he or she. Okay, yeah, he has either like in person or like online session to help you out. Yeah, make sure you figure out how to solve those problems, those homework problems. And also it's better to go through your slides. Yeah, that's what I have to say about preparation for the exam. Yeah, I'll edit the exam again to reduce the number of questions, because right now it has like, so each answer you input is 2 points. So right now I have like 60 something, 60.
Including the sub questions?
I mean, those sub questions, like each input you have to put in, it's in total it's 60. But now I'm thinking to reduce it to maybe like 40 to 50.
I'm asking you, because you go to the level, you're asking us more examples.
Yeah, during the lecture. I see.
Yes,
I see.
that's
Yeah.
my question.
Yeah, I agree. Yes.
I think somebody asked me in the chat. I was gonna ask you the same. The first one.
Is it only one try question? Oh, this one?
Yeah.
Say
the one they write.
Yeah, the exam will happen only on during class time, like on next week Wednesday from 5:30 to 8:15. Yeah. And it's only available during that period. It's,
right?
yes, through WebAssign. It's not one try question. Oh, I forgot to check. So for the homework, you have 3 tries. I'm thinking maybe put 3 try for the exam as well. Do we have to be in class? No, you can work at home. Yeah, you can work on it at home. Yes, our students. It's kind of on your honor to work on it, but it's timed. It's not like you can spend the whole afternoon, yeah, working on it.
We don't have the lockdown.
No, I think in that way you will not be able to use our, yes. Yeah, 3 tries.
I think emphasis should be focused on using how to solve this problem.
Yes.
So that we know this command line that we use when we face this kind of problem. But we haven't been doing much of that. Like I had to learn that from them or from my teaching assistant. And it would be very helpful if we like start learning all these things so that we can start applying it to solve the problem.
Yeah, that's what I'm trying to do, but yeah, sometimes it's very hard. That I think from your perspective, and it's good that you have your input, like you telling me like like your hope, like how will this be like. Yeah, this is also my first time teaching like this, so Yeah, so I'm trying to improve like the teaching as well. So any input, any suggestion are welcome.
I find looking through the drop downs the most helpful. The R markdowns.
Okay,
That's
yeah,
just me personally.
the our like lab examples.
Yeah, how we do it in class, like I find myself looking back at which.
That's kind of my logic. I was hoping that those R examples will be like helpful for you guys to solve homework problems, but maybe that's not like. Yes, yeah, okay, yeah. So I'm thinking, yeah, we can get more like R examples. Either works through some of the homework questions. Yeah, we'll do that. In the future, like starting from, I think starting from chapter 8. Okay, so let's just start with today's lecture. Well, today's lecture, like this confidence interval material will not be included in your exam 1, but it's definitely will be in our next exam, which exam 2. And this is like the essential part of statistics, confidence intervals, and tests. They are very important. Okay, let's get started with this. Oh, slideshow. Oh, where is the?
Oh, you can just press on the top next to the
Oh,
save.
yeah, I see that. I see this. Okay. All right, and last chapter we talked about estimates, point estimates, but we kind of mentioned it when we have only one point estimate. We are not able to tell like how sure, how certain, yeah, how sure we are with this estimate. So I have listed here like why we go from estimates to intervals. So I give you an example here. A sample size of 3 probably does not give you a good estimate. I give you just do a point estimate. But we use this confidence interval to convey the how confident we are with the estimate. So confidence interval have the center being your point estimate. So it's kind of it has a lower bound and upper bound being an interval. Like the wider the interval is, you are more uncertain about the estimate, right? I have this. So instead of just one value, its confidence interval give you a range, a likely range for the estimate. So if we estimated the mu hat, or say x bar is 6, so we estimate this mu being 6. Comparing these two intervals, either we say this confidence interval for this parameter mu is from 5 to 7, or we say confidence interval for mu is 5.9 to 6.1. So this one is much narrower comparing to this one. That means we are more confident to get a guess for this mu with this narrower interval. So the weights of this interval tells the difference about our confidence in this point estimate. I think this kind of makes sense. If someone asks you, make a guess, what's the difference from from this building to that building? Well, if you say as like it can be negative, right? You say from 0 to infinity, then you kind of saying nothing. But if you say a very narrow or specific range to it, that means you have some confidence on it. You kind of know where it is. It's not like everywhere. So we use this confidence interval to to tell the story behind our estimate, to show how confident we are with it. And to come with this confidence interval, we have this alpha called confidence level or significant level, to adjust how sure we want to be. Common levels for alpha is 0.1, 0.05, 0.01. Well, alpha being, I have a note about this significance level. We calculate the interval so that it will include the true value 1 minus alpha % of the time. So alpha being 0.05, that means it corresponding to a 95% confidence interval. So this alpha is the significance level, and it corresponding to 1 minus alpha % confidence interval. Well, the confidence, the meaning of this interval is that we get the interval so that it will include the true value 95% of the time, and it won't contain the value like 5% of the time. The value for the significance level is adjusted depending on the situation. When you are in a, like, you are trying to measure the average shooting percentage of a basketball player, getting the wrong value being like alpha being 0.1, which corresponding to like 10%. 0.1 is okay. You get a 90% confidence interval corresponding to an alpha being 0.1. But if you are looking at the average tumor response to a new drug, maybe you need to be a little more sure, like to downsize your alpha a little bit, like either use 0.01 or 0.05, but 0.1 is kind of big in this situation. Normally what you hear is like 95% confidence interval or 90% confidence interval. Okay, the confidence. So this is just repeat again what is the actual meaning of this interval with this alpha level. If alpha being 0.05, we are 95% confident with your interval. The higher the confidence interval, the more strongly we believe the true value of the parameter is in that interval. And there is a formal kind of, it's very easy to get confused. It's not saying the probability that your estimate following that interval being 0.95, but we say like if you repeatedly doing the experiment or whatsoever, doing the sampling, if you're repeatedly doing this, the percentage of the time that your estimate would follow in that interval is 95% of the time. Okay, how do we find this interval? So we have a lower bound and an upper bound, and we find the value L and U, like representing lower bound and upper bound, so that this probability of your random variable X within this lower bound and upper bound, this probability being 1 minus alpha. So we can find this because we know the distribution of this X, right? So once we know the distribution of this X, we can work on this probability. It's kind of finding a quantile after giving this 1 minus alpha, like finding your 90th quantile, or like 2.5 quantile. We'll see that in a minute. And for this lecture, we will only do this confidence interval for the mean and proportion. It's the most typical estimates, and we learned about it previously, like get the point estimate for those. So we will do the confidence interval for this one, for these two, But theoretically, you can do confidence interval for any kind of estimates you have. Okay, so this kind of give you an intuitive like understanding of what this confidence interval is. Like if we look at a PDF, is that, well, for a confidence level being alpha, then this area is alpha over 2, like on this two tile being like alpha over 2 is the area under this PDF line. And this is the 95, 1 minus alpha percent, like following in between. So our confidence interval being XL and XH, so that 95% of the time, our estimate would follow in this interval. Like if we repeatedly drawing samples and calculate or estimate, this is corresponding to the 95% of them following this area. And if we look at from a CDF perspective, is that CDF is telling you like the probability something is less than a bond. So this 1 minus alpha of the time is like in this area, where on the left tail of the CDF, you have also like alpha over 2 for this probability on this y-axis. And on the top, you get another alpha over 2 probability in this area. So this is the area in between that have you the probability of your values following this XL and XU. It should be XU, like upper and lower. Yeah, so we find this XL and XU such that the area under the curve between those points is 1 minus alpha.
So you said we could use the quartile function to find it.
Yes.
So basically, whenever, like, let's say we found 1 minus alpha, we can put in the Q norm and it'll come out.
Yeah, that's how that's how you're going to find it. We'll go to those formulas in a minute. This is just to kind of connect you with the PDF curve and CDF curve you learned before. So our goal here is to find this XL and XU. So we find this, yeah, we learn those formulas for this, I think it's for the mean, yeah, for a normal distributed random variable. There is a known variance for this scenario. We are going to find confidence interval for a normal distributed variable, and we know the population variance. You will see the formula in a minute. So let's see, we are working on a standard normal distribution. So the probability of, if this standard normal, we still denoted by Z, and Z greater than negative 1.96 and less or equal to 1.96, this probability is 0.95. So this negative 1.96 and this 1.96 is the corresponding like upper bound and lower bound we are trying to look for this standard normal distribution. So this is the value we are trying to find out. But here it's known for standard normal, like either by looking up the table, you'll figure out, okay, oh, this is negative 1.96 and the upper bound is positive 1.96. I didn't tell you how to like do the like table lookup, but if we, I think it's, let's get to that maybe like, yeah, I think I put the coding stuff in the very end to how to calculate odds. But this is something you should get yourself really familiarized.
So on the homework, whenever asking questions like this and put the absolute value of Z,
Yes,
would that give the same, I guess?
yes, like let,
interval?
yes,
Okay,
yes. So Z, but we normally put it in this way.
right.
But you can also like put the absolute value of Z less or equal to 1.96.
Okay.
It's the same meaning. But this is something new, something you should know for standard normal, because standard normal is kind of, we know the mean is 0 and sigma is 1, and this is always true. But if you are told about if you are asked about the standard normal, the confidence interval would always be like this. And we use this one to find the confidence interval for other random variables which follows normal distribution. Like for x, now we can transform. We know the z, the link between z and any of this random variable x. Like this x bar minus mu divided by its standard error, it's just equal to z, which is the standard normal. So we know the link of them. We can now transform. We just use this to replace the z. And we know this is always true for standard normal. And we do a bit of reorganize this inequality, right? We get this mu will greater than this value and less or equal to this value, and this probability is being 0.95. So this is how we find this confidence interval by this truth that we know for standard normal, it's always like this. Either, yeah, we can work on the quantile like coding to find out this is true. But this will be given to you, and this is how we get for parameter mu, which is the mean value. This is how we get. I think you guys know how we get this from this. You just like multiply this thing over here, and then this x bar would go like x bar minus this whole thing, and the same for this side. This is how you get this. So we have this x bar minus 1.96 sigma over square root of n. This is for mu. We get this confidence interval, 95% confidence interval. Okay, so this is the formula for 95% confidence interval for mu. A side note for this is that we use this x bar being as the sample mean as our point estimate, and now we get this confidence interval for our parameter mu. So this x bar is our point estimate for mu, and this is the confidence interval for mu. Okay, so yeah, I think this is kind of just reiterate what we said previously, but we normally denote this previously we have this 1.96 corresponding to alpha equal to 0.5. But for alpha being a general value, we use this z alpha over 2 to denote it's actually called a critical value, but you will see that definition in the text when we do hypothesis testing. So for now, you just need to know we use this z alpha over 2 to denote the quantile for the alpha over 2 quantile for a standard normal. So, and then we use this notation for a 1 over alpha, 1 minus alpha percentage confidence interval for the mean would be our point estimate, x bar, plus or minus this z value times the standard error of this x bar. So it will be, actually, it's a general formula that you put your point estimate in the center. So it will always be the point estimate plus and minus the critical value times the standard error of your point estimate. But here you just need to know for this, for mu, this is the formula to get the confidence interval. So this z alpha over 2, this is how you get it. The probability of z less or equal to this value being 1 minus alpha over 2. I hope you know how to get this z alpha over 2 by, like, when alpha being 0.05, then you just find the, I think it's 97.5 quantile for your standard normal. Just plug in the alpha value to do the calculation, in R to find this small z alpha over 2. Yeah, this is how we do it in R. As your confidence interval level change, see, it might not always alpha equal to 0.05. You will need to, well, now you know when alpha equal to 0.05, then this value z 0.025 will be 1.96, right? That's what we used for the standard normal. And when alpha change, you would have to go to R to find it out. So this is the old command you use to find the quantile. But make sure you know the argument you put for this Q norm is 1 minus alpha over 2. Because the Q norm is corresponding to a CDF, which is always on the left-hand side of your, it will be always like on the left-hand side of this, would be like this, less or equal to something. So, and this is the probability it corresponding to. So you have to put this 1 over alpha, 1 minus alpha over 2 as the argument for Q norm in order to find this value, z alpha over 2. So this command is to find this value. Oh, well, for normal distribution is symmetric. The value would be, the absolute value would be the same if you do this Q norm alpha over 2, because you remember it's a bell-shaped curve on the 97.5 percentile and the 2.5 percentile. Their absolute value are the same. It's just minus and plus. Remember the minus 1.96 and the positive 1.96. It will be like this. But yeah, just do not mess up the plus or minus. But when you do an interval, always the smaller number would be the lower level. The larger number would be the upper level, upper limit. So now I think you get the formula, like how did we get, everything is from here, and how do we get this, like in general, how do we get the formula for a parameter mu? And then we figure out if the alpha not equal to 0.05, how do we find this value to plug in this formula? So this is only for 95% confidence interval. When alpha not equal to 0.05, you need to find out what is this z alpha over 2 by yeah, you find this Z alpha over 2 by this command in R. Okay, now let's go through an example. I think I have this. Let's just go through this. We are measuring cat weights. We weighed 30 cats and find a sample mean of 15.6 pounds. A sample mean. Now you can write down X bar equal to 115.6. Yes, exactly. This is how you like solve a problem. You have to write something down before you go to R. It's known that a cat weight have a standard deviation of 0.7 pounds. After reading this, you know you can write sigma equal to 0.7. Oh, did I say 0.6 or 0.7 pounds? Find a 90s confidence interval for the mean weight of cats. Now it's asking for the 90s confidence interval. You know alpha is 0.1, right? Alpha is 0.1. Remember, alpha is 1 minus like 90s, which is 0.9. So alpha equal to 0.1. Let me just give you the formula, which is X bar, you already find out, and sigma, you already find out, and alpha, I said alpha equal to 0.1, and sample size n, you also know that n equal to 30. Now what's now known is this Z alpha over 2, you go to R to find, yeah, I listed, this is how you do, yeah, you're supposed to write this down and then go find what this D alpha is. You do this Q norm. Well, this 0, 1 is by default being the mean and standard deviation. This is how you find this critical value, Z alpha over 2. Note that you put alpha here, alpha equal to 0.1. And then you plug everything in, you got your interval. Yeah, I think this one is the same as the R lab I have. Like, yeah, I think for when you do coding, this might be a trick. You might find it's handy or not. Like I name it. See, this is the same statement as what we saw in the slides, and I name those value. I do not just use R as a calculator where you put this this values in, but but you name those variable. This is n, this is your X bar, or yeah, X bar, and this is your sigma, alpha, and then now you get the Z by just put this alpha here, because sometimes you could just forget, like either it's alpha over 2 or whatsoever. But this is normally what I do for this, and well, point estimate is this X bar, so it's always this point estimate. Well, I think we'll go over this error band a little bit later, yeah, this is how you get the Z value and plug in to this error band. We'll define this error band in a minute, and you get the error band, and this is how you get the lower and upper limits for in R.
The error bound is just the standard error, right?
Yeah, the error band is this value, Okay, yeah. So what this, I think this is kind of related to that. What happens when we change the confidence levels? What need to change to be 99.9% sure we've got the right answer versus being 80% sure? So that's our confidence level change. And then how would your confidence interval change? So the more we are sure about something, our confidence interval, like,
It's more narrow.
yeah, like what happens to, oops. Let's just do it. Oops. Yeah. Just do it real quick.
This is more.
Yeah. So this is alpha being 0.1, right? Being 0.1 is 90%, 90% confidence. But if we want 80%, yeah, then we want 0.2, and we get this different z value. Actually, if you do, let me just get you to this upper level and lower level. This is for okay. Oh, this is really 15.4, 15.7. But if you do alpha, what happened?
The lower bound came a little bit closer.
It's getting, oh, do not get yourself confused about the confidence level and the like. So the confidence level is alpha.
Yeah.
But when I see 90% or 95%, that's 1 minus alpha. So it's like the opposite. So if I increase, or what I did is I decreased. Okay. Anyway, like I decreased from 0.2, alpha being 0.2. It's give you a narrower confidence interval. But when I decrease the alpha, it gives you a wider confidence interval. So that's alpha. It's the opposite with the like 95 or 90s confidence interval.
Oh, because you're including more numbers to be more likely to include the actual.
Yeah, yeah. So this is the 90% confidence. Yeah, this is the 90s, and that's the 80% confidence interval. Oops. And what will happen if we change the sample size? I think this one is easier. If we decrease the sample size, this whole thing will increase, right? So when this bond increase, then your interval will be wider.
So it does the same thing, not that increasing and decreasing out.
Yeah, and or when you, well, I think it's better to see it from, oops, let me just do this. See it from here. Yeah. So yeah, I think for when you change the confidence, when you change alpha, let's see, when we change alpha, like if this current value here is for alpha point equal to 0.05, but if we decrease alpha, see this area will be smaller because like the more you get more upper.
Oh, right, it's not.
Yeah, it's getting.
Alpha's the one that's not.
Yeah, it controls like how farther away you go from the center of this standard normal. So when your alpha increase, this area corresponding will be smaller. So you go further to the line. That means the value of this like z alpha over 2 will be bigger. So yeah, when this Z alpha over 2 is bigger, then, well, then this whole thing is bigger. So you get wider confidence interval.
And the same thing happens
When you decrease.
When you decrease that.
Yeah, when you decrease the n, the sample size. I think this is straightforward. If you go and goes up or goes down, you know the weights of your interval will change which direction.
Wait,
So
I'm sorry, can you go back to that? You said if the sample size decreases,
yes, okay.
Sorry.
Well, why it's always from.
That'll do it, yeah, that's just.
This is slideshow from current slide. Okay. Well, example about controlling the size with different sample size. So we know that we know the average standard deviation of temperature is 0.5. Sigma equal to 0.5. We want to estimate the mean temperature to within 1 degree with 95% confidence. Within 1 degree. So we want to estimate the mean temperature to within 1 degree. That means this error band. Did I define this error band? Yeah, this is called the error band, like this thing. Not sure if it is strange. I thought I defined it, but I mentioned it anyway. So, whoops. Yeah. So this is your error band. How can we decide how many people we need to measure to get that accuracy? So now we're trying to determine n. And it says we want to estimate the mean temperature to within 1 degree. Within 1 degree is telling you this probability of your estimate mu is less or equal to, yeah, the absolute value of your, the absolute value of your x bar less or equal to 1. Yeah, that's your, that's the error band equal to 1. This is telling you. So yeah, this is your error band equal to 1. That means we are trying to find n in this case. And z alpha over 2, you know how to find it. Once this number is given, you get alpha being 0.05, and sigma, you already write it down as 0.5, and you just find n. I think it will be straightforward once you get this and this. This is one type of question you will see in your homework. One type would be find the confidence interval. Another is like, you know, the error band and you find the sample size, but you always play with that one formula, like this, x bar plus or minus this thing.
So it would be Q norm 1 minus 0.05
Over
Yeah.
2.
over 2.
Yeah.
And then that'll give us the number and then just plug everything else in and solve
Yeah.
for
Yes.
0.05. That's 95 is 0.95.
Yeah, 95% corresponding to 1 minus 0.95. So that's 0.05. Yes. Yeah, 0.05. Okay. So previously we were always dealing with, we know the sigma. So now what if we do not know the sigma with unknown variance? With unknown variance, we if you guess, we would just use the sample standard deviation with a small s, right? So, well, let's go from the slides. If you have a small sample size and don't know the standard deviation, you can get bad estimates if you use normal distribution. The bad estimate, I mean, your estimate will be too good. That's you're kind of too sure about your estimate. It's actually not reflecting the actual situation. So that's a bad estimate. Well, we got previously we were dealing with standard normal. Now we have to make a little bit tweak on that, where we use a distribution called student T distribution. Well, it's developed by an East scientist to work with when we have small sample size, or like when your distribution is not so normal, we just use T distribution. Well, T distribution is very similar to a normal distribution. It's also symmetric and bell-shaped. It's hard to tell, but T distribution is supposed to have heavier or thicker tails comparing to a normal distribution. So it's both are like bell-shaped and symmetric. It's just this T distribution have a thicker tail. Yeah, so this is what we get to when we do not know the standard deviation of the population. So when small sigma is unknown, we use this S from our sample, which is a sample standard deviation, and we use T distribution instead of normal distribution to get our critical value, just like the Z alpha over 2. Now we use this T alpha over 2. But it has this for T distribution, you have like one parameter being the degree freedom of this T distribution, and it's n minus 1, where n is your sample size. Yeah, for T distribution, it only got this one parameter, degree freedom, and it's n minus 1. So for normal distribution, we have two parameters, right? Mean and the standard deviation. For T, we only need to specify its degree freedom. So everything would still apply. So it's the same logic. How did you get the confidence interval? By like rearrange this thing to get the interval from a probability perspective. And from R, you just do this QT instead of Q norm, and also specify the degree freedom for this. And but other things are work the same. You just replace this normal distribution to T distribution. And you still specify 1 minus alpha over 2 to get the Z value, sorry, the T value. Now it's the T value T alpha over 2. Okay, and yeah, student T confidence interval. So very similar as in the normal situation, we take, this is kind of our standard normal. Previously, that's the standard normal. Now we use this. This follows the T distribution. Now we rearrange this inequality to get this 1 minus alpha confidence interval. This is the same thing, just going from normal distribution to a T distribution. And note that this is when you do not know the population variance or the population standard deviation. But you can get this S from your sample, which is your sample standard deviation, this S. You need this S and this T value to get your confidence interval. Well, there's another example for the student T. 7 different flavors of chips were randomly selected at the store. The mean fat gram per serving was 7.5. The mean is 7.5, and the sample standard deviation was 2.1. So now what the information you have? X bar equal to 7.5. This is the mean, and the sample standard deviation, that's your small s. S equal to 2.1, and assume and 7 different flavors, that's your sample size, and n equal to 7. Yeah, n equal to 7. Normal population, yeah, the underlying, I haven't read this. Assuming the underlying distribution is approximately normal, your distribution of this, like fat grams per serving is normal. What's a 90% confidence interval around the mean fat grams per serving? Well, okay, we know the data is following normal distribution, but unknown variance. It didn't tell you the population variance, it told you the sample standard deviation. And you're assuming you do not know the variance, population variance. Now we use the student T for this value. Note that this big thing follows a T distribution when we have X following normal distribution, but with unknown standard deviation. Unknown variance, yeah, unknown standard deviation. So the T distribution is for this quantity. And this normal distribution says the underlying distribution is approximately normal. It's talking about this X, like the fat gram. Yeah. So we know this information, and we need to get this T alpha over 2. This is how you get it from R1 minus alpha over 2, and given the degree freedom being n minus 1. Okay, and then plugging everything, you get your confidence interval. 90% confidence interval, alpha being 0.1. Yeah, I think this is the same. Yeah, I think it's the same. Right, I have this all code up in R just for your reference. This is how I do the calculation. Well, we've talked about this population mean, like we're trying to get a confidence interval for mu. But now what about the population proportion confidence interval? So now we want to work on a confidence interval for P, which is the population proportion. And P is the unknown population probability of success in a binary experiment. So we should say this: we know our random variable is X following a Bernoulli distribution, and this P is going with this Bernoulli distribution, and we want to get this confidence interval for this P parameter. So we do sample lots of this X and estimate P with this P hat, where this P hat is the sum of X value, and X can only be either 0 or 1. That's your binary experiment. This Bernoulli, yeah, X is Bernoulli, it's always 0 or 1. You sum them up, and 1 divided by n. N is the number of times you run, either you flip a coin. So Well, this one actually use the central limit theorem if n is large enough. Central limit theorem give us that when we have a large enough sample size, we can approximate the distribution to a normal distribution. So we have this conclusion that when n is large enough, we know this p hat is following a normal distribution with this mu and this sigma divided by square root of n. And this mu is actually this, we estimated by p hat. And the sigma, if you still remember for, hopefully I didn't confuse you, this x is, x is a Bernoulli, x follows a Bernoulli distribution with probability p, and this q, I put it here. So use your, so the q I put here is this 1 minus p hat. Actually, if you recall, this is related to a binomial distribution, right? X following Bernoulli, but when you sum them up, like you run them n times, you get a binomial distribution with n being your times of the times of your experiment, and p would still be the probability of success. So if you go back to your notes, you will find this formula for estimate of your standard deviation for a binomial distribution, which is p times 1 minus p divided by n. That's the standard deviation. That's the variance for binomial distribution. But if you do not recall, this is the value. I mean, this is kind of the formula I gave to you. This probability p is having this distribution. This is by central limit theorem. When you have large enough sample size, you can approximate this sample proportion to a normal distribution, and with p hat being the mean and this being the standard deviation. And now you know as this is the normal distribution, and now you can just use the confidence interval related to confidence interval for this p is p hat, that's your point estimate for p, and plus or minus this critical value z alpha over 2 and times the standard error. Okay, this is just another kind of formula for you for if you are asked about the confidence interval for p, population proportion. Okay, but I mentioned the central limit theorem where it's asking for a large enough n. So in order to apply this formula, we have to have some like kind of requirement for n. So from the text, it says, from your textbook, it says n times p hat should be greater or equal to 10, and n times q hat, which is 1 minus p hat. So this value should be greater or equal to 10 as well, in order to get the central limit theorem to hold. So I think there might be, there will be homework questions on this. Just pay attention that it has a requirement for the sample size in order to use this formula, in order to get this confidence interval for this. I said you need to pay attention to the sample size in order to apply this formula to calculate the confidence interval for the population proportion p. Okay, so one. So this is another example. So in my sample of 30 students in my classes, 14 have pets, 16 do not. So this kind of related to a proportion kind of thing. Use this data to estimate the proportion of MSDA students. So that's a large population, right? I'm just use my own sample to estimate this population proportion. So we want to get the 95% confidence interval for this proportion. So whenever you see proportion, you're going to work with the confidence interval for P. When you see mean, like the mean weight or mean something, that's you work with the like mean, which is the X bar or mu confidence interval. Okay, so for this one, well, estimate the proportion of students who have pets. So from my sample, my P hat who have pets is 14/30. Yeah, so when you see proportion, you use this formula and you figure out what is P hat. 14/30, and Q hat is 1 minus P, so 16/30. And the sample size is 30. And get this Z alpha/2, and yeah, this is handy. If you remember, for standard normal, like Z alpha/2, when alpha equal to 0.05, it's always 1.96.
So you don't have to use QT because you have everything. Right?
Yeah, for this one, it's just a normal, normal distributed. Because you have like large enough sample size for this to work. And plug everything you got your
Question, for the sample size, when you say large one, it's supposed to be more than 10.
oh, n times p hat should be greater or equal to 10, and n times q hat also greater or equal to 10. So yeah, you have to kind of verify, but this is the only formula we have for p hats. Normally it's asking you if it's okay to do this confidence interval. You just need to verify if the sample size satisfy those requirements. Suppose in my last class only 2 of the 21 students had a pet. Can I estimate a confidence interval for this proportion and for this population proportion? Yeah, so in this case, is obviously it's asking if it satisfies the requirements for n. Yeah. You just need to verify. Okay. How do you know which one to use? Actually, I only gave you kind of 3 formula, but you will definitely get overwhelmed if I give you all those formulas. It's more than 3. You will you will go crazy when you see those formulas. How do you know which one to use? Well, yeah, the choice of formula for confidence interval depending on the sample size, distribution of the population, and whether or not you know sigma, which is the population standard deviation. I have a slide summarized, contains a breakdown of when to use which one. So now it looks a bit overwhelming already, but it's not really. Let's see, for a normally distributed population with known sigma, you use this formula. This is the first one we learned. We know everything. Like for a population from any distribution with unknown sigma and n large enough, so you can use this formula. And you kind of have to just to verify if it's like those conditions were met or not, in order to pick the right formula to use. Population from any distribution with unknown sigma and large enough n. You can kind of approximate with normal, but use this S sample standard deviation to replace your sigma population standard deviation. For a normally distributed population with unknown sigma, you use this T. Pay attention. I didn't mention this in our previous slides, but I think it could come in homework questions. So this is what I gave you is the normal distributed population with unknown sigma. So we talked about this case and this case in our slide. But if the population is from any distribution, I didn't mention that your random variable is following normal distribution, you might have it just fall into this category.
Sure.
Yes.
I was thinking of what about the dimension type of distribution?
Yeah, if it's not mentioned, you have to assume it's unknown. But if it mentioned in the statement where we know it's approximately normally distributed, now you know it's normal distributed and you choose the scenario for this. For population proportion with data from Bernoulli distribution, like binary, and satisfy these two conditions for the sample size, you can go with this formula. Well, this is for population variance, sigma square. But this is the confidence interval that I didn't teach in this lecture. Well, I just listed here for you, just in case, because for it has really many more like confidence interval formulas, but I only gave you this 3 from the lecture today, but there are way more. Yes, I think this one, I don't feel like I have question about this population variance because I didn't talk about this. Yeah. Let's see. Let me see this. Yeah, I feel like this is just give you our version of the examples that we just went through. Anyway, yeah, I attached this R markdown file, and also, yeah, I feel anyway, the Blackboard is not open, but it's uploaded on, yeah, I will upload on Blackboard. Okay, that's it for this week. Yeah, you can spend more time preparing for the exam and get back to the material after the exam. I probably will post the homework for this lecture after the exam. So before the exam, you prepare for it. After that, you might relax a bit, but you still got homework to do. This is, yeah, I would say this is how statistics go. Everyone have to go through. You go through this, you learn it, you have to practice by working on it. Yeah, maybe it's not that annoying when you get familiarized with all this and you go to industry working as a data analyst. At that time, you will feel better because you already get a grasp of the knowledge. So when you are a graduate student or undergraduate student, it's kind of a pain to go through the process. Okay, that's it for today. Yeah, seems like there's no other questions. If no questions, oh, let me see. Oh, why is the homework due? Chapter? Okay. Well, I think I kind of thought about it. I was hoping that you finish your homework a bit early so that you get a larger chunk of time go through the slides. Well, at the time when I gave you the homework, I thought there are plenty of time for you to work on the homeworks. So I just changed.
We have other courses that we're doing.
Hmm?
We have other courses that we're doing also.
Oh, yes.
So that actually fits into our times.
Okay. Yeah, I see. So if you like Saturday better, I can put like for future like homeworks, I can always put Saturday. Yeah, it's a bit strange, right? All previous homeworks are Saturday due time, but this two are Friday. Do you need extension for chapter 5 and chapter 6 to extend it to Saturday? If that's needed, let me know. I can extend the deadline for homework. Okay, yeah, I'll do that. Just make sure you got some time to review your notes. Yeah, it's lots of information, and I have to admit it's boring. Even like when I learned this, I felt, yeah, it's kind of started when I was in my undergraduate. At that time, I'm not in statistics major. I was in industrial engineering. It's all mathematic kind of thing. But when I first learned this statistics probability, I felt sorry about the professor at that time. Oh, why? This is so boring what you are talking about. But when I get to this position, I feel, oh, this is just what it is. This is like all the knowledge you have to kind of go through, lots of things to remember. Yeah. Well, good luck on the exam. Yeah, I'll try to reduce the number of questions. Okay, let's just stop here.